Well, no, we'll get our homework from last night, page 268, specifically two questions, 8 and 10. Number 8 says a 1,500 kilogram car is making a turn with a 100 meter radius on a road where the coefficient of static friction is 0.70. What's the maximum speed of the car can go without skidding? We've done a few questions like this before, right? Doesn't mean it's easy still, but we've done a few like this before. We know whenever the object is going around in a circle, we know that there's a few things that we can do. V is equal to 2 pi r over t. A is equal to v squared over r. F is equal to mv squared over r. Since we're talking about static friction, friction force, okay, we're probably going to use the force equation. Fc is equal to mv squared over r. But I think what we're going to find in this question is that we need to also know that Fc is caused by Ff. Remember that centripetal force is always caused by something. In this case, friction. We don't always need to remember to know that, to notice that, or to pay attention to that, but sometimes we do. If we just try solving for this using mv squared over r, we're going to have too many unknowns. So then we have to do something else. What's the else? Well, the friction force. So we're going to say here that centripetal force, mv squared over r equals mu times the normal force, which is m times g. Masses cancel, and I'm looking for the speed of the car at that point. The r goes up by multiplying, and then we square root it, mu times g times r. So we get, 0.70 times 9.81. We just drop the negative there, times r is 100. And we square root that, and what do we end up getting there? And number 10 says NASA uses a centrifuge that spins astronauts around in a capsule at the end of an 8.9 meter metallic arm. The centrifuge spins at 35 RPMs. We want to draw attention to this RPMs because we know that we want to use a frequency in hertz, revolutions per second, as opposed to revolutions per minute here. Determine the magnitude of the centripetal acceleration of the astronauts experience, and how many times greater is this than the acceleration due to gravity. They do this for real. So does the Air Force when they train fighter pilots. They put you in the centrifuge, the end of a 9 meter long, basically this 9 meter long thing that spins around, and they spin it faster and faster and faster, so that at some point the wall pushing you in, the centripetal force pushing you in, ends up becoming bigger and bigger and bigger. At some point, the centripetal force pushing you in is the same as the force of gravity pulling you down. And then when we spin it faster, it's twice as big. And then it's 3 times as big, and then it's 4 times as big, and so on. And basically what they're trying to do is make you pass out. They're trying to see how fast they got to spin this thing, how many G's you've got to experience before you pass out. Okay, if you pass out at 2 G's, you probably fail the fighter pilot test. Okay, passing out at 2 G's, you would not make a very good fighter pilot or a very good astronaut. Okay, if you make it to 7, 8 G's, then you're probably going to be okay. Okay, if you pass out at 8 G's, then you're probably going to be okay. Not too many people make it past 8 G's without passing out, literally without passing out. All right, so what are we going to do here? Well, like any other question, like we want to try something that's valid. Like somebody, well, actually, let's write down some givens, and then we'll get somebody to tell me something that's valid here. We've got a radius of 8.9 meters here, and we've got a frequency of 35 RPMs, although we do want to convert that to a frequency in hertz. We remember that because we circled it in red, right? We had drawn attention to it. In hertz, that would be what, 35 divided by 60? I think it was 0.58 something. Who's got that? 0.58? 0.583 repeating, thank you. We definitely want to be in hertz or revolutions per second. The magnitude of the centripetal acceleration at this point, forget about the second question right now. Just what's the magnitude of the centripetal acceleration? Tell me something. Like, what do you know here? Tell me one thing that I can do. If you give me something valid, it doesn't matter if it leads you to the right answer. At least it's something. Liam, what's something that I know about this question? Beyond the givens, right? Like an equation, a concept, or something. Yeah, you do. Sure you do. Sure you do. Look up here. What are we looking for? What kind of acceleration? Okay, so what do we know about this? Tell me something, some equation that I know about this that's going to be valid. A is equal to v squared divided by r. Now, when you look at this, you're looking for the centripetal acceleration. Odds are that's what you're going to use to find it, right? But even in the end, if it doesn't work out to be the equation that you want to use to solve for, it's valid. Okay, don't ever sit at your desk or sit at home on the couch or wherever you're doing your work. Don't ever say, I don't know an equation. Yes, you do. Yes, you do. Okay, sometimes we just got to try a little bit harder and go a little bit further and think about it a little bit more, and you do. We always do. Now, you might not be able to solve the question. Fair enough. Okay, I'm not expecting everybody to get 100, right? But everybody can at least write down something that's valid here. A is equal to v squared over r. Is there anything else? Anybody else catch anything else that I might want to try here? Braden?
You can try to find what the velocity is.
Okay, so v is equal to 2 pi r over t. Is that going to be helpful to me? I'm not sure. Probably is, since I want v in here, but it's valid, right? Right, Liam? It's valid. Okay, whether I use it or not. Anything else, Jen? Okay, so we get the period from the frequency. T is equal to 1 over f. We know the frequency, so let's do that now. We couldn't do this one or this one yet because we're missing something, but we know what f is, so let's figure out what the period is. The inverse of 0.5833 gives me what, Jen? 1.79 seconds. Okay, good. Good. Helpful? I don't know, but it's something and it's right. Okay, it's right. If we were asking about the situation in this class and you said Adam's shirt is orange, maybe that's not helpful to us when we're trying to solve whatever problem we're dealing with, but it's correct. So there's no harm in writing that down. Okay, we just found the period. Maybe it's not helpful. Maybe it is, but there's no harm in it either way. I got a feeling, given that we have found the period and somebody else told me that 2 pi r over t is applicable here, I got a feeling that we can do something else. Brogan? 1.71? Okay. 1.71, not 1.79. But we can still use that up here, right? 2 times pi times 8.9 divided by 1.71. What do we get for the speed there? Who has that? Yep. 32.62 meters per second. Well, now we can plug that back, Liam, into here, 32.62 squared divided by r, 8.9. Now, I hope you don't make a mistake like forgetting to square that, but that happens from time to time. Okay, there's an excuse for that, right? We're careless sometimes. We make a mistake. None of us are perfect. Okay, but we don't have an excuse for not writing anything down. We all know something. Okay, now, 2 weeks ago, you would absolutely have an excuse for not writing anything down for this question, right? Because you didn't know anything about circular motion. But now that we do, we all know enough about it to write down some equations that are valid at the very least. 119.55 meters per second squared. We're going to actually round that to 2 digits, 1.2 times 10 to the 2 meters per second squared. The reason I kept that, the 119, is so that I could find this. How many times greater is the acceleration than the acceleration of gravity? All I'm going to do here is say 119.55 divided by 9.81. And that gives me 12.2, or 12. It's 12 Gs. So the odds of this astronaut staying conscious through this 12 Gs is effectively 0, or very, very close to 0. People just don't withstand 12 Gs for any more than a tiny fraction of a second. Now, that doesn't mean the astronaut would die, but if that astronaut experiences that for 2 or 3 seconds, the astronaut would almost certainly pass out. Okay? All right, if we've finished 1 to 10, let's give you a few minutes here right now to work on questions 11 to 15. You're going to find that as we go further, they get a little bit more challenging, especially question number 14, I think. But remember, as you're going through all of these, 11, 12, 13, 14, 15, then have your data sheet in front of you. Have example questions in front of you. think about what you know about this. Is there an equation that I know? Is there a concept that I know? Is there a unit conversion that I've got to deal with? And you got a fighting chance at all of them. Okay, let's see what you can do. Then we'll get a couple more questions now. Number 12 says, determine the acceleration of a person, it's centripetal acceleration acting on a person standing at the equator. Not as hard as it seems, actually. We don't have very much given to us here, Braden, but we do have a little bit more if we read between the lines a little bit. Here's my radius, the radius of the Earth, which of course I'm standing at the equator, so that's the distance that I am away from the center of rotation. What else do I have given to me here if I read between the lines? What else do I know about this situation? Yep. Yeah, I know the orbital period here. If I'm on the Earth and I go around the Earth once, then the period of my rotation would be 24 hours. 24 hours times 60 gives me minutes, times 60 again gives me seconds, and it works out to be 86,400 seconds. So that's how long it takes to go around the circle once, for me, standing on the surface of the Earth at the equator. I'm looking for the centripetal acceleration. We may have struggled with this, okay, of getting that period. That's okay. Okay, but we all know, even if we struggled with that, we all know that we have to write down a is equal to v squared over r, because we're looking for centripetal acceleration. So write that down. We know that we have to find v, oops, not v squared over r squared, right? V squared over r. We know that we have to find v, and that's probably going to happen by 2 pi r over t. All right, now it's looking really important that I recognize what the period was. 2 times pi times 6.38 times 10 to the 6, divided by the period of 86,400 seconds. What's v work out to be there? It's pretty big, I think, wasn't it? Like 4,000 or something? No, sorry, what was it? Yeah, that's right. Yeah, that's right. 400. 463 point. Okay. Yeah, I don't know why I was thinking 4,000. I remember from this morning that it was about 1.5 times the speed of sound. 4,000 would be like 15 times the speed of sound, right? How can we be going so fast and not notice it? Well, A, we're not going that fast because we're not on the equator. But we're still going fast. How can we be going fast like that and not even notice it? Yeah. Everything's going with us, right? The desk that you're sitting in is moving at that speed too. If you were moving at 463 and your desk wasn't, well, then you'd notice it. If the air was moving at 0 and you were moving at 463, then you'd notice it. That'd be a pretty strong wind, right? A 463 kilometer an hour wind. But since we're all moving at more or less the same speed, we don't notice it. Let's sub that in now, 463.9667. Square it, divide it by r. And I think that works out to be a really small number, 0.003 or something like that. 0.03. Keep going. Did you write it down? Meters per second squared. Now, this is the acceleration that we need in order to stay on the Earth. What happens if we don't have that? What happens if nothing supplies that? We fly off into space. Is there something that supplies that? Yeah, and then some. What is it, Jordan? Gravity, right? Gravity can supply up to 9.81 meters per second squared centripetal force. It supplies a lot more for us. We don't need that much gravity. That is, in order to stay on Earth, we don't need that much gravity. But we need that much gravity for other things, just not to stay on Earth, not to fly off into space. 13, an ant climbs onto the side of a bicycle tire at a distance of 0.4 meters from the hub. The 0.010 gram ant can hold onto the tire with a force of 4.34 times 10 to the negative 4. What's the frequency? At what frequency would the tire fling the ant off? R is 0.40 meters. My mass is, I'm going to say 0.010 times 10 to the minus 3 grams. Some of you guys may just prefer to move the decimal place over. I like to use the exponent there. Whatever, it doesn't really matter. we're looking, we've got force, the centripetal force. And we're looking for the frequency here. Okay, tell me something. Liam, tell me something I can do here. You don't have to give me something that's going to give me the answer. I'm not asking for that. I'm just asking to give me something that I can do here. Good. Frequency is 1 over the period. T is equal to 1 over F on our data sheet. We rearrange that, we get F is equal to 1 over period. Okay, we don't know the period. That's okay. Maybe we find the period, maybe we don't. Okay, if we do find the period, then perfect, that works out. If we don't find the period, then oh well, you gave me an equation that doesn't work, but it was valid. It was a correct equation. Okay, anything else? Anything else that'll help you to find the period or anything else that's valid? Yep. Okay, so F is equal to mv squared over r. Of course that's valid because we're moving in a circle. And we can find v this way, so let's do that. V becomes equal to F times R over M, and then we got to square root that. So it becomes 4.34 times 10 to the negative 4 times R, 0.40, divided by the mass, 0.010 times 10 to the minus 3. And we square root that, and what does V end up being equal to there, Maddie? 4.16 meters per second. All right, so there's speed. Okay. If you're able to find speed, it's probably going to be used here. Okay, it's unlikely that we're going to get this far with this equation to get speed if it's not relevant to us. But worst case scenario is we just found speed and it's not useful. It's not a big deal. It just means a little bit of work that we maybe didn't have to do. Okay, now what? Yep, agree? Good. Let's say 2 pi r divided by t. That'll allow me to find the period, right? 2 pi r divided by v. So we've got 2 times pi times 0.40 divided by the speed of 4.16. Bree, do you have what that equals? 0.604 seconds. And look, now, goes back to what Liam gave me at the beginning, F is equal to 1 over t. Okay, I got the period here. Frequency is 1 over that. And that gives me, who's got that now? 1.66 hertz. Okay, is that okay? We want to get this point across to you that, like, even when you think you don't know how to do something, like, we've always got a fighting chance, unless it's one of those insane questions. But generally, we've got a fighting chance. Okay, we just have to not give up, and then most times it'll work out for us. Okay, if we don't give up on it. Not always, but most times. It will. Okay, 14. This one says 2 pulleys are connected by a belt. The motor spins at 200 RPMs. So we're gonna call this one number 1, this one number 2. We're gonna say F1 is 200 RPM. What is that in hertz? 200 divided by 60 is, what is that? 3.33? Okay, so F1 is 3.33. Oh, look, they gave me a big hint here. Both pulleys have the same velocity at their outer edge. That's quite true, actually. They've made a mistake with that. They're close, but both pulleys do not have the same velocity at their outer edge. Both pulleys have the same speed at their outer edge. Velocity is always changing because of direction, right? But the speed is the same. All right, so let's say this. Let's say if object number 1 has the same speed as object number 2, let's set them equal. Like, they tell me that, right? Well, we know that 2 pi r for number 1 over t for number 1 is equal to 2 pi r for number 2 divided by the period for number 2. Oh, I can find the period for number 1, right? 1 over 3.333. What's that? 0.3? Exactly 0.3? 2 times pi times 0.10 meters over 0.30 seconds equals 2 times pi times 0.25 meters divided by T2. That's what we're looking for, isn't it? Oh, no, we're looking for the frequency, but once we find the period, we can find the frequency using F is equal to 1 over T, right? That's a harder question. Okay, that's a harder one. I always tell you guys, look, we can always write down something that's valid. You know what? There's things you can write down here that are valid. V equals 2 pi over T and so on. But to make that next step of setting those equal to each other, that's a tough one. Okay, so if you struggle with something like that, all right. As long as you get the other 9 questions and you have a little bit of trouble with this one, then we're good. T2 works out to be what? T2 goes up. Oh, it's kind of ugly rearranging. 0.3 goes up. Oh, 2 pi cancels, doesn't it? That saves me a bother. T goes up. 0.3 goes up. 0.1 goes down. So I end up with 0.25 times 0.3 divided by 0.1 gives me a period of 0.75. And then the frequency is 1 over 0.75. That's 1.3. Yeah. 1.3 hertz. Should be actually 1 point. Yeah, just 1.3 is right. Okay, how many people ended up getting that? Okay, tricky one.